In the previous section, we looked at different graphs in three-dimensional space, and we had an x, a y, and a z coordinate. In this section, we're going to talk about what it means for z to be a function of the variables x and y. So we can explicitly solve for z and write z as a function of x and y. For example, let's say we have z equal to x plus y minus 1. Well, then we can go ahead and replace z with our function notation. So z is a function of x and y, which is equal to x plus y minus 1. Well, sometimes we don't explicitly solve for z. Sometimes we use the implicit form, would just be setting the equation equal to 0. So in the equation that we had previously, I can go ahead and subtract z from both sides and write this equation as x plus y minus z minus 1 equal to 0. And then I can replace with my function notation. So now this is a function of x, y, and z. And that would be equal to x plus y minus z minus 1. And we're going to use these two forms as we go through Calculus 3 and Calculus 4. So let's look at the explicit form, where z is written as a function of x and y. Well, if z is a function, it's going to have a domain. The domain of z are the points x and y that we put into our function. When we put x and y into our function, the range, what we get back, is the z values. So it's appropriate when we talk about functions to talk about domain and range. Example 1, we want to find the domain for our function. Remember, this is just a z value, equal to the tangent of x plus y. So tangent is undefined at pi over 2 plus k pi multiples of pi over 2. So as long as the argument x plus y is not equal to pi over 2, I'm okay. And then plus k pi. So I can write that the domain of my function f, and here I'm going to use my shorthand for domain, DOM, of f. That would be equal to the set of all points x and y such that x plus y is not equal to pi over 2 plus any pi multiples, because pi is a period of tangent. So any k pi multiples of pi over 2. But whenever I introduce a new variable, I need to say what it is. So here, k is any integer. So I'm going to write k is an integer. And then close my set braces. So that is my set, which is the domain. The way we describe the domain is not unique, as long as it's sufficient. So I could also write this as the domain of f. It's going to start the same, because I'm putting in points x and y such that I could say that x plus y cannot be equal to, think about pi over 2, 3 pi over 2, 5 pi over 2. That's where tangent has its vertical asymptote, so it's undefined. But it's also undefined at negative pi over 2, negative 3 pi over 2. So it's undefined at k pi over 2, where k is an odd integer. And that's why it's important to describe the variables that you introduce. So this would be another way that I can describe the domain. Now let's look at example 2 and find the domain for our function h of xy. And that's a natural log function. So you have to remember that log functions are never negative, they're never zero, they're always positive. Well, what we put into them is always positive. So as long as x squared minus y, as long as this argument is strictly greater than 0, then I'm okay. So I could write that the domain of my function h is the set of all points x and y such that x squared minus y is greater than 0. Or I can isolate the y and have y less than x squared. So I can also write this as the domain of h, which is all points x and y, such that y is less than x squared. It's nice to look at a picture when we're dealing in three-dimensional space. Remember, in two-dimensional space, a function has to pass the vertical line test. That's the same in three-dimensional space as well. So functions of two variables must also pass the vertical line test. What that means is that every line parallel to the z-axis passes through at most one point. So let's look at this. In my domain, I'm putting in some point x and y. What it's going to do is going to give me back a z value on my surface. So if I pick any point at all in my domain, it's going to give me a value, a z value on this surface. So z is a function provided that any vertical line I draw passes through at most one point on my surface. What that means is that each point x and y in our domain will lie on the graph of f. So every point in the domain has a corresponding z value. Alright, so in example 3, we're going to find the domain and range for this function g, and we're also going to sketch the graph. Well, first of all, when I find the domain, remember that my g of x, y, that's my z value. This is a square root function. It can be 0, it can be positive, but it cannot be negative. So I have to make sure that the square root of 1 minus x squared minus y squared is greater than or equal to 0. And if I square both sides, I have 1 minus x squared minus y squared greater than or equal to 0. Great, so that is my domain. But I want to graph this domain just to see what it looks like. So I'm going to try to get this in a form that I recognize. I'm going to subtract 1 from both sides and then multiply through by a negative 1, remembering to flip my sign. And then looking at this graph in the x and y plane, not in three-dimensional space, I can see that this is a circle centered at the origin with a radius of 1. The domain is the circle and everything inside, because it's all x and y less than or equal to 1. So that would be my domain, which is the set of all points x and y such that x squared plus y squared is less than or equal to 1. So now I want to find the range. So this is z squared equal to the square root of 1 minus, if I factor out the negative, I get x squared plus y squared. And I know that my x squared plus y squared is less than or equal to 1, which also tells me that x squared plus y squared is greater than or equal to 0, right? Can't be negative because I'm squaring the x and the y. So since these values are between 0 and 1, I get my range as well. Notice when I write my range for my function g, I'm not writing ordered pairs because the range is simply a z value. It's a single value. And since my x squared plus y squareds are going to go between 0 and 1, then I know that the square root, right? So I'm putting those values into my function. So if I put in x squared plus y squared between 0 and 1, well, if x squared plus y squared is 0, z is 1. If x squared plus y squared is 1, z is 0. So I know that my z values are going to range from 0 to 1. So that would be my range of g. What this is the upper half of a sphere centered at the origin with a radius of 1. Because my domain is this circle, so I just sketch my domain, and I know my z values go from 0 to 1. And there's my attempt at drawing I guess it's a half of a sphere. So I know my sketches are pretty bad. But let me go ahead and draw my intercepts. I have 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so since my sketches are pretty horrible, what I'm going to do is describe this as the upper half of a sphere centered at 0, 0, 0, at the origin. Okay. Ooh, of radius 1. That's important. So I just knew it was because I saw that equation, but how did I get that? Well, I know that z is equal to the square root of 1 minus, I'll keep it as the parentheses of x squared plus y squared. So if I try to write this in a form that's more recognizable, what I want to do is square both sides to get z squared equal to 1 minus x squared plus y squared. Now if I add the x squared plus y squared to both sides, I have x squared plus y squared plus z squared is equal to 1, which is simply a sphere of radius 1. The next topic that we want to talk about when we're looking at our functions is level curves. Now remember, our z function is some surface in three-dimensional space. So if we look at this diagram, we see our surface z, If we take our surface and we intersect our surface with a horizontal plane, then what we get is a contour curve. So that would be this curve in green. Now we can take this contour curve, which is on our surface Z, and we can project it down into the XY plane. So if we take a contour curve and we project it down into the XY plane, that is what we call a level curve. And you've probably seen this when you look at topographical maps, how they have those level curves or contour curves. So a level curve is simply a projection of a contour curve onto the XY plane. So the equations of these level curves are simply our Z value equal to some number. Okay? So the Z naught is a constant in the range of F. Oftentimes it's easier for us to work with level curves than it is for us to work on a three-dimensional surface. Example 4, we're going to sketch the level curves of our function g of xy equal to y minus x squared minus 2. So the first thing I'm going to do is I'm going to replace this function g with my z value and write z equal to y minus x squared minus 2. And then I'm going to replace my z values with numbers that are in the range of z. It might be easier if I just make a table. So let's say that our z value is 0. If z is 0 in my equation, this becomes 0 equal to y minus x squared minus 2. Rearranging, I get y equal to x squared plus 2. And I know what that is. That's a parabola. So when z is equal to 0, I get the equation y equal to x squared plus 2. This is a parabola opening up. It has its vertex at 2. And this happens when z is equal to 0. If z is equal to 1, we get y equal to x squared plus 3, which is a parabola opening up with its vertex at 3. Okay, so this is 3, this is 2, 1. Now I can see that if I look at larger values of z, I'm going to keep getting parabolas that are opening up, but the vertex is going to go from 3 to 4 to 5 and so on. So let me look at what happens if z is negative 1. If z is negative 1, y is equal to x squared plus 1. And I can see that, oh, that was a sad parabola, sorry. I can see that this is a parabola that's still opening up. But now we're getting closer and closer to our origin. And then if I put in negative 2 for my z value, I get y equal to x squared. And that's how you graph your level curves. All you do is take your equation and you replace your z value with numbers that are in the range of z. So if I had to describe the level curves are parabolas. And if I wanted to be more specific, I could say their vertex is on the y-axis. All right. So we've talked about functions of 2 variables, functions with 3 variables. Now we're going to look at functions with more than 2 variables. So the process is the same. The problem is let's say we add some w. So now our equation has an x, y, z, w. The problem is I don't know how to graph that. I know how to graph, barely know how to graph in 3-dimensional space. But once I'm in 4-dimensional space, that's a little weird. However, we could still do the math there. We could still find domains. So in general, if you look at this table, if you have one independent variable, then y is a function of the one independent variable x. That would be the explicit form. Implicitly, it could be a function of x, y, and we could set it equal to 0. So the graph would be in the xy plane, 2-dimensional space. If you have 2 independent variables, z is written in terms of the 2 independent variables, x and y, or implicitly we can write it as a function x, y, z. That would be in 3-dimensional space, or x, y, z space. 3 independent variables, we'll call it w, and it's going to be some function of x, y, z. Implicitly, it would be a function w, x, y, z equal to 0, and that would be in 4-dimensional space, and so on. So for any n number of independent variables, we're going to have a function of n independent variables, or we can write it as n plus 1 in implicit form, and that would be in the r to the n plus 1 space. Again, I have no idea how to draw that, but it's fascinating that we can still do the math there. So something to note is that level curves are when you take a surface in 3-dimensional space and you drop it down to the xy plane, 2-dimensional space. So if you have a function of 3 variables, then instead of a level curve, you're going to have a level surface. Again, kind of hard to wrap your mind around that, since we're dealing in dimensions that we're not very familiar with. But let's go ahead and see if we can find the domain of a function with 3 independent variables. So example 5a, this function f, that would be like my w value. And it's equal to the square root of 9 minus x squared minus y squared minus z squared. So it's a square root function. I know that whatever's under this square root has to be greater than or equal to 0. So I'm just going to take all of this and set it greater than or equal to 0. And this kind of reminds me of a sphere. So I'm going to throw the 9 on the other side, multiply through by a negative to get x squared plus y squared plus z squared less than or equal to a positive 9. So I'm just writing it in a form that I recognize. So I recognize this as not just a sphere. I recognize this as a ball. So the domain of my function f is going to be the set of all ordered triplets x, yz such that x squared, plus y squared plus z squared is less than or equal to 9. And describing this, that would be a ball, which we had talked about in a previous section, centered at the origin 0, 0, 0 with radius 3. Okay, let's try another one. Let's look at this function g. It's equal to 1 over x minus z. So this is a fraction. I have a problem when the denominator is 0 on a fraction. So I know that x minus z cannot be equal to 0. All other values are fine, just cannot be equal to 0. Or in other words, x cannot be equal to z. So the domain of my function g is a set of all ordered triplets x, y, z. And notice that in the definition of my function, there's no y value there, which is fine. I know that it's an ordered triplet because that's how the function is defined, such that x is not equal to z. So if I were to describe this domain, it would be all points in R3. So all points in three-dimensional real space, so R3 except x equal to z, that's a plane. So except the plane x equal to z. Okay, so that's it for this section.